Welcome to the live session 3 of the course Reagents in Organic Synthesis. So in the Google form there is one question that I will explain first. So the rate of hydrogenation by Wilkinson catalyst cis alkene higher than trans alkene. So if you have a cis alkene, suppose we consider the same substituent for cis and trans. So this is the cis alkene and this is the trans alkene. Now this hydrogenation is a syn addition. So syn addition means both hydrogen will add from the same site. And in Wilkinson catalyst, so hydrogen first coordinates with catalyst. So what will happen when catalyst is coming from this side, because you see this R and R dash are on the same side. So the catalyst with hydrogen will add from this side, okay? So it will face the less steric hindrance. On the other hand, for transalkene, what will happen? Transalkene, so if the catalyst can come from this side, okay, then it can, we are thinking that it is coming from the same phase, so then it will steric repulsion from the R group. On the other hand, from this side, it will have the steric repulsion from the R dash side. On the other hand, for cis alkene, since R and R dash on the same side, catalyst can easily approach from this hydrogen side. Okay. So we are thinking that if you think that the plane it comes, and now if it is coming from the top or down, okay, then it may not feel the steric repulsion, but this is also possibility that it can come from this phase, and that way the syn alkene cases the catalyst feels less steric repulse. Okay, that might be the reason. So another important reaction is the surface epoxidation. And allylic alcohols getting epoxidized, right? Allylic alcohols getting So epoxidized, and of course this is the chiral version, that's the surface developed. So chiral catalyst. And what is the chiral catalyst? That is generated in situ, and that is formed from titanium isopropoxide, titanium actually 4 here, and diethyl tartarate, diethyl tartarate. And diethyl tartarate can be L or D, okay, and L is actually plus, so that is called plus, and D is called minus. So I draw first the structures of this diethyl tartarate. So L, which is plus date, that can be drawn like this. So you can draw CO2 weight. Okay, like this you can draw the CO2 from the same side actually. So this can be also drawn like this. If you draw CO2 group in the plane, so here OH groups on the plane, then also you can draw like this. So then it will be like this. So one molecule can be drawn in many ways. So this you can say is equal to. Also you can draw zigzag. That also you can draw. And in the zigzag, what will happen? This OH will move. If we give the rotation, then this up OH becomes down, and your CO2 comes here, and so this is the L plus date, and the other one, its enantiomer is actually minus isomer, and that is D, and that is called minus date. And exactly now you can draw the enantiomer. So wherever chiral center is there, you have to draw just the opposite one. So here minus was there, so we can draw plus. Now this OH group, this will be up and this will be down. And this is the zigzag orientation. Okay, now I will discuss the facial selectivity. So if you draw allylic alcohol like this way, so you have to think that this CH2OH at the lower right side. So lower side you have to draw. Now you have to draw lower right or left, okay, accordingly. Now this alcohol is in the plane, okay. So all groups are in the plane. Now D minus tartarate, so D minus tartarate or date, okay, tartarate or D minus date, that will approach from the top side, okay. So that will attack from the top side, and you know what will be the product, so you can draw the product also if he attacks from the top side, and later we will discuss by example. So top side means like this you have to draw. And minus L plus date, so L plus date that will come from the lower side, and that one, so this is the A, suppose, so this is the A and this is the B approach. So in the B approach you get this product. Okay, so then when you draw in the lower right, so CH2OH group, CH2OH group, so this is the case 1, CH2OH group in lower right. So this is the plane, but you see this CH2OH group in the lower, okay, if you think that this is higher lower side and right side. And in this case, the minus date will attack from the top face, so this will attack from the top face, and this will be down face. Now we will see that exactly opposite will happen when CH2H group in the lower left. So case 2, lower left. Now the same molecule you can draw. Okay. CH2OH, R3, R1, this will be. So you see your CH2OH group in the lower, so this is the lower and left side. Now what will happen? Now exactly opposite will happen. So L plus date will attack from the top side. So this will be case 1, A case, okay, the top face attack. So in the top face attack you get this epoxide with L plus date, and now if you react with D minus date minus diethyl tartarate, then the attack will take place from the lower side. So this is the top face attack, this is lower or down face, down face attack. And you get this alcohol. It does not matter, you can draw this epoxide this side also, okay, because you want to just show the face of the epoxide. So then you get this product. So when your alcohol CH2OH group in the lower left side, then plus date will attack from the top face and minus date will attack from the down face. And we discussed already, when it is lower right side, then the minus date will attack from the top face and L plus date will attack from the down face. So this you have to remember. So if there is any question, you can ask me now. If there is any question you can ask, otherwise we will close. Okay, I think. Okay, thank you. I hope you will enjoy the course, and we are closing here, and all the best for the final exam.